Okay, so hello everyone. Welcome back to your Comp 335 tutorial. This is your third tutorial. And if some of you are freaking out because of the date here, I lost the recording for this tutorial when I originally did it, so I am re-recording it. But that shouldn't really be a problem. I haven't really changed the content, so it should still be relevant. So what we'll be discussing in this third tutorial, which is going to be split into a couple of videos, is first of all, we're going to quickly review some notions of DFAs, deterministic finite automata, which we looked at in the previous tutorial. Then we're going to look at minimal DFAs. So what does it mean for a DFA to be minimal? This isn't something that is always covered in the lecture. So a tutorial is a good reference to look for when it comes to problems about minimizations of DFAs. And then after that, we'll be looking at non-deterministic finite automata, so introducing non-determinism in your FA. And also we'll see essentially the equivalence between NFAs and DFAs with the NFA to DFA conversion algorithm. So these two are going to be individual videos, and this together is going to be in the video you're watching right now. Okay, so enough explaining. Let's just get right into the material. So let's do a quick review of DFAs. So we have the following exercises here. As usual, I encourage you to pause the video and try these questions out yourself. Take maybe 1 or 2 minutes to try to ponder them, and we'll look at them together. Okay, so hopefully you've had a second to look at the questions, at least read them. So the first exercise here, exercise 1, is a infamous true or false question, where the statement that we want to see whether it's true or false is given a DFA M with states Q, alphabet sigma, transition function delta, initial state Q0, and the set of final states F. So given this DFA M, if the language accepted by M or L of M is the empty set, that is, the DFA does not accept any strings, then the set of final states, so the set F, must be empty as well. Okay, so this one is a bit tricky. It's actually going to turn out to be false. Okay, and the reason for that is because I can create a DFA M that is essentially using final states, that has some final states, but that still has the language accepted being empty. And how can I do this? Well, essentially what I can do, for instance, is I can start in my initial state Q0 and make the initial state a trap state, or remember, it's like a black hole. So I make it a trap state by making this a non-final state, and by saying, if I assume my alphabet is AB, by saying, excuse me, by saying that any string that enters this DFA is essentially going to be trapped here. Okay, so essentially you can think of any string over the alphabet AB, it's always going to stay in here. So once the input finishes, the input is going to terminate on a non-final state, which means that if this was M, then I hope you would agree that L of M is the empty state, is the empty set, sorry. But so now what I'm going to try to do is I want this to be true, right? I want L of M to be equal to the empty set, but I want the set of final states to be non-empty. Okay, so essentially I want to add a final state. So how can I do this? Well, what I can do is I can essentially add a dummy or useless state final state. It's called Q1. So it has the double circle, meaning it's final state. And it has, remember this is a DFA, so it has exactly two transitions where if you're in Q1, which can never happen, but let's say, just for the sake of the example, that if you're in Q1 and you see an A or B, you go to Q0. And this is in fact a valid DFA. It respects this definition here, right? Q would be Q0, Q1, sigma, your alphabet is well defined, it's AB. The delta function is this transition function. There's nothing wrong with this transition function. Your initial state is well defined, right? The initial state is the guy with the in arrow here. And you have a set of a non-empty set of final states. In this case, you have Q1. So this is a valid DFA. So this is why it's a bit of a trick question, because not a lot of you might have thought of this example initially, which is fine. I mean, it's okay to at first be stuck on a question. But now that you've kind of seen this, you can see that you can essentially add these types of states here, these types of states, which are known as unreachable states. So they're unreachable because if you start in Q0, and of course we know that every computation starts in Q0, so every computation in your DFA can never reach or never passes through Q1. So that's what we mean by unreachable. Or in other words, if we took this, so if we kind of took this transition and this state here, and we removed it from the DFA, we would get essentially the same DFA as before, meaning that the new kind of cut out DFA without the unreachable state would accept the same language. Okay, so this is why this guy is in fact false, because I can add an unreachable state and it remains a valid DFA. And this is a nice way of introducing the notion of unreachable states, which is going to be used, which is a notion that's going to be seen when we want to minimize our DFA. Okay, so hopefully for exercise 1, that's clear. Now, exercise 2, we were given a DFA here, a pretty simple DFA. Well, that looked pretty simple, and we wanted to describe the language accepted by the DFA. So if this was M, we wanted to know what L of M was. Okay, so in this case, we see that our initial state, Q0, is a final state. So the only string that, so suppose W is any string over, let's say, our alphabet. Well, in this case, we need to assume our alphabet is AB. So let's say our string goes into Q0, as it does for kind of any DFA. The only way that it can stop at Q0 and then be accepted by the DFA is if W is the empty string, lambda. Because remember, for a DFA, if it reads the empty string lambda, what happens is essentially your machine doesn't move. It just stays at the same place. So your lambda here enters the DFA, and then it just stays, or it gets essentially stuck in Q0. But for this kind of DFA, that's good, because then it accepts lambda. So here, lambda is accepted. But now if we take any other string but lambda, so essentially any other string that is non-empty, for instance, if we take A, then we know that if we want to read our string, we need to kind of move forward in our DFA, or essentially use a transition. So if you're in Q0 here, so you start the input here, but then you have to read your A here, so you read your A, then your machine must essentially transition from Q0 to Q1. And the same thing can be said for any other string like B or BA or AAB, and so on. Every other string has to transition to Q1. And then once you're in Q1, I hope you can notice that this is now a trap state. Remember, it's like our black hole. Nothing escapes the black hole. Nothing can get out of it. Anything or every string that enters this trap state is going to essentially be rejected. So lambda is accepted, and essentially every other string is going to be rejected. So what this allows us to say is that the language accepted by M is going to be the set that contains lambda, or the set that contains the empty string. Okay, so this is one kind of special DFA. Remember, we had a couple of languages that were quite important in this course. We had the empty set as a language. Then we had the universal set, or sigma star, as a language. And finally, we had the set containing lambda, or the language containing only lambda as a language. And these were important because they had some interesting properties that no other language essentially had. Okay, and so we just saw what the DFA for accepting the language containing the empty string is, and you've probably already seen in the lecture what the DFAs for the empty string and sigma star are. But for sort of just the sake of completeness, I just want to remind you that a DFA, so a DFA, meaning that this notion of uniqueness is not true. So it's not unique, but a DFA for the empty set, let's say, and in fact the simplest DFA for the empty set, and simplest we're going to define in a couple of seconds, but the simplest intuitively DFA for the empty set would be you have your initial state, and you just make that initial state a trap state. So similar to the example we did here, except that I removed that unreachable state, and now I have a single state here. And that single state, the initial state, is a trap state. So it's kind of like you enter your machine, and for any input you get, you enter the kind of black hole or the trap state. So everything is rejected, right? So everything meaning any possible string. So that implies that the language accepted by M, if this is M, is the empty set. But notice I did say A, so remember I said this was not unique. And the reason why it's not unique is I could create another DFA, let's say this guy here, and this is Q1, this is Q2. This guy here is an equivalent DFA in the sense that it accepts the same language, the empty set. Okay, and I hope you can see that because none of these states are final states, and you don't have any kind of unreachable states that you have to sort of consider. So all of the computation that's occurring is occurring in non-final states. So that means that you can never accept, or your machine is never going to accept a string if it has this kind of configuration. And then similarly for sigma star, so for the universal set or the universal language, if we're assuming that our alphabet is a B, like I did here, so here I was also assuming that the alphabet was a B. Okay, then the simplest possible DFA, again, we don't really know what simplest means, but we'll define that in a second, would be you have your initial state, you make that initial state a final state, and you do a self loop over all of your alphabet on Q0. So what this says is that for any string W that is inputted in your machine M, that W is essentially going to go through all of its computation in this state, and it's going to always end in Q0. And because Q0 is a final state, that means that any string, so for every string in sigma star, W, that string W is accepted. So then by definition, that means that the language accepted by M is sigma star. And again, this is a DFA. It's not unique. There are many such DFAs that could accept sigma star. Okay. And I encourage you to think of a couple of other examples for that. I mean, it wouldn't be, you could essentially just convert all of the non-final states here into final states, and that would be another possible DFA. Okay, so I hope that helps with the kind of review of DFAs. If it wasn't already clear through the tutorial 2 videos and through the lecture videos, hopefully this sheds a bit more light and kind of gives you a different angle or perspective on DFAs, because these kinds of questions can kind of pop up in I would say, potentially pop up in quizzes, or essentially questions like this that make you really think about the definition, that really make you try to, how can I put this, that want to make sure that you really understand the definitions of DFAs, that you really know what's going on in a DFA and what the possible DFAs are. Okay, so hopefully that's the goal. Really, I hope that it was helpful in doing that. If it's not, I would sort of suggest sending the TAs some emails, trying to ask more questions to get that clarified. Okay, so that was for the review on DFAs. Now that we've done that, we're going to tackle minimal DFAs and the minimization of DFAs. Okay, so minimal DFAs. What do we mean by minimal DFA, or what do we mean by the simplest? So sorry for my calligraphy, but for the simplest, what do we mean by the simplest DFA? Well, we just saw before that, for instance, for the empty language, or for the sigma star language, so for the language containing all possible strings, there are several DFAs that can accept it, okay? And in general, given a language, there are several DFAs M that can accept that language. However, we have a theorem here that tells us that for every regular language, and in fact, here actually, for the most picky students, this should actually say, given a regular language L, there are several DFAs that accept it, because it wouldn't be true in general if I had just said, given a language L, and maybe in a few weeks, check back on this particular moment, on this particular kind of mistake that I just made, and kind of try to realize why what I just said was wrong if I didn't say regular language, okay? But for now, let's just say that there wasn't a typo there, and that it said, given a regular language L, there are several DFAs M that can accept, okay? So we have a theorem here that tells us that for every regular language L, there is a unique minimal DFA M hat that accepts it. And we define M hat as being minimal in the sense that there does not exist any other DFA with a smaller number of states that does the same job, that is, that accepts the same language. So what I mean by that is, let's say I have this language L that is regular, and I want to generate or create a DFA that accepts it. Okay, so maybe one student is going to create a DFA M with, let's say, 6 states. Okay, and then maybe another student is going to come and he's going to create a DFA with a bit more states. So let's say with 8 states. And then maybe another student is going to see maybe a shortcut, and he or she is going to generate, is going to draw or create a DFA with, let's say, 5 states. And essentially the list can go on, but this theorem tells us that in fact there is a unique a number of states. So there's a unique minimal number of states that any DFA, given a language, a regular language has, that will accept it. Okay, so meaning that for a particular regular language, there exists a minimal number of states for a DFA to accept it. So perhaps in one example, in one instance of a particular language, so for a particular language, perhaps the smallest number of states to accept that language could be 3. Or then maybe for another language, it could be 5 because the language is slightly more complex. Okay, so it all depends on the language, on the regular language. So depending on the regular language, that tells you what the minimal number of states required will be for a DFA to accept that language out. And this becomes quite abstract if you look at it this way, but there is a essentially kind of rigorous and kind of methodological argument and algorithm that allows you to, given first of all, that given a DFA M, there exists an algorithm that allows you to convert it to a minimal DFA M prime. Okay, so the minimal DFA, the converted minimal DFA would be equivalent, meaning that L of M should be equal to L of M prime, but the number, so let's say the number of states of M prime should be less than or equal the number of states for N, okay? Because this is going to be your minimal DFA. And then once we've defined the idea or the notion of minimal DFA, then we can say, we can then, so once we kind of define this, which we're going to do in this algorithm that you just saw as a sneak peek there, once we define the kind of minimization of DFAs, then we can answer a question like, given a language L, what is the minimal DFA that accepts it, or what is the minimum? This is a question that might sort of occur in a test, that might easily kind of occur in a test because it's easy to use as an MCQ. So it would be something like, what is the minimum number of states in a what is the minimum number of states? It's a bit long to write. Minimum number of states required to accept the language L. Okay, so that's another question that we could answer once we see this kind of minimization algorithm. Okay, so let me stop kind of floating around the idea and actually tackle it directly. So the minimization algorithm that I'm talking about, where you're given a DFA M and you sort of plug it into your algorithm and it outputs an equivalent minimal DFA M hat. That is, the languages accepted by both are the same, but M hat will have a number less than or equal, a number of states less than or equal the number of states in M. So that's the idea of the minimization or state reduction algorithm. and there are a few steps. So this might look a bit complicated, but trust me, it's a lot easier than it looks. Okay, so there are a few steps involved in this minimization algorithm. So remember, suppose you just have a kind of black box algorithm. So you have a state reduction algorithm. You input your initial DFA M, and what's supposed to output is the equivalent minimal DFA M hat. Okay, so how does that happen? The first thing that the algorithm tells us to do, so this is step one, is that we want to remove all unreachable states in M. Okay, so remember, unreachable states, those are the states that when you start in Q0, no matter what the input string is, there is no computation that goes to that state. So I gave you an example before with that true-false question where I had this initial state here that was a trap state, and then I had connected to it another state here with this kind of transition. I mean, it didn't need to be necessarily a transition like that. It could have been something like this. This guy would have still been unreachable. And in general, if you just kind of look carefully, it's pretty easy to spot which states are going to be unreachable. Try a few strings and see which states are never kind of going to get hit by those computations. And in general, that should be enough to spot all of the unreachable states. Okay. The second step, so this is where you're going to get in the kind of bulk of the computation, the real computation of the algorithm. And the second step is you want to initialize two sets, or I'm also going to call them two partitions. There's going to be more than two at some point, but for now there's only two. So you're going to initialize two sets, two partitions. S1 is going to be all of the non-final states. So that's why it's Q different F. And S2 is going to be all the final states. Okay. So you've set up your two partitions, S1 and S2. The next thing you need to do is for each pair of states in each partition, so that's two kind of for loops. It's for each pair PQ of states in each partition S1, S2, you need to determine whether or not P and Q are indistinguishable or distinguishable. And if they're distinguishable, you're going to essentially split the partitions, and if they're indistinguishable, you're going to combine the partitions. But I don't expect you to understand what I mean by combine and separate right now. It becomes a lot clearer with the example that I'm going to present. But for now, what I want to essentially explain to you is what I mean by indistinguishable and distinguishable states. Okay, so to do that, I have an extra kind of an extra mini slide that's not in the official slides of this tutorial. That's hopefully going to help me explain to you what I mean by distinguishable and indistinguishable states. Okay, so suppose you have the situation here where you're in your kind of state reduction algorithm, and you have a DFA M here over the alphabet 0, 1. So your DFA has a bunch of states. It has some non-final states. It has some final states here. And in particular, what I'm interested in is I'm interested in two states, Q1 and Q2. For the purposes of this example, I've made Q1, when it sees a 0, go back to itself, and when it sees a 1, go to Q4. So Q4 is another state in your machine M, in your DFA M. And again, for the purposes of this example, I have another state Q2, which when it sees a 0 also goes back to itself, and when it sees a 1 goes to Q3. Okay, so that's my setup. I don't really care what else is in my DFA. I'm only focused on the pair Q1 and Q2. And the question is, I want to know whether the states Q1 and Q2 are indistinguishable or distinguishable, okay? And another piece of information you need to know before you try to start answering this question is you want to know what partitions each state belongs to. In this case, I've said that states Q1 and states Q2 belong to partition S. Okay, so S is some partition. There could be more, but just for the sake of this kind of explanation, I'm reserving my partitions to S and T. Okay, so S is the partition that contains Q1 and Q2, potentially other states, I don't really care. And T is the partition that contains states Q3 and Q4 and potentially other states. Okay, so I need to know what states what partitions each of my states that I'm focusing on belong to. Okay, for this kind of indistinguishable, distinguishable idea to work. Okay, and so when are states Q1 and Q2 indistinguishable? They're indistinguishable if for each symbol little sigma, right? So that's a symbol, little sigma is a symbol, in my alphabet big sigma, okay? When Q1 sees the symbol little sigma, it goes to the same partition as when Q2 sees the symbol little sigma, okay? So in other words, when Q1 and Q2 see the same symbol, they should go to the same partition, all right? So maybe let's write that as an aside. If Q1 and Q2 for each symbol sigma see if for Q1 and Q2 when they see the same symbol, so in other words, sigma, they see the same symbol sigma. If Q1 and Q2, when they see the same symbol sigma, they go to the same partition. Okay, if this is true for every symbol, so notice I'm not saying that Q1 and Q2 for each symbol should go to the same partition. So I'm not saying that if you have Q1 and Q2 for 0 and 1, they should both go to S. I'm saying that for Q1 and Q2, when they see a 0, they should go to the same partition. And for Q1 and Q2, when they see a 1, they should go to the same partition. Okay, that's all I'm saying. I'm not saying that these two should be the same. I'm saying for a particular symbol that Q1 and Q2 see, they should go to the same partition. Okay, so now let's see if that's the case for this example here. So remember my setup here. I have two symbols that I need to check because my alphabet is, as a reminder, it's 0, 1. So I need to check for the symbol 0, whether Q1 and Q2, when they see a 0, go to the same partition. And so that's for 0. And then for 1, when Q1 and Q2 see a 1, do they go to the same partition? So let's check. So the transition function of Q1, when it sees 0, so if you're in Q1 and you see a 0, you go back to Q1. But Q1 is part of partition S, so I write that Q1 belongs to S. Okay? Then I do the same thing for Q2. When Q2 sees a 0, it goes back to itself, Q2. So in other words, it goes to Q2. But Q2 is again part of S. So when Q2 sees a 0, it's part of partition S. These two are the same. So far, it looks like Q1 and Q2 might be indistinguishable. Okay. Now, if I go to the second symbol 1, I essentially repeat the same process. When Q1 sees a 1, it goes to Q4. So when Q1 sees a 1, it goes to Q4. Then when Q2 sees a 1, it goes to Q3. But both of these are part of partition T. So both of these are part of partition T. So when Q1 and Q2 see a 1, they go to the same partition. Because they go to the same partition, for 1, they appear to be indistinguishable. But now because for 0 and for 1, Q1 and Q2 go to the same partition. So remember, I'm not saying that these two are the same. They don't need to be the same. But for a particular symbol, so for 0, they go to the same partition S. For 1, they go to the same partition T. So that means that together, the states Q1 and Q2, sorry, are indistinguishable. So Q1 and Q2 are indistinguishable. If it had happened that Q3, instead of being in T, so let's say Q3 instead was in S. So if this was in S, then these two would not be the same. So the partitions for a symbol 1, for the symbol 1, for Q1 and Q2, they wouldn't go to the same partition. So then you would have a break in this definition here, right? Because this says that for each symbol, it has to be the same partition, okay? So because you don't have that condition anymore, then they would become, if essentially this case was occurring when Q3 was part of S, then they would be distinguishable instead. Okay, so that's the idea of indistinguishable and distinguishable. I understand that for now it might not seem super clear why I'm talking about this, but it's going to be clear when I look at the algorithm in a few seconds. Okay, so if you're still a bit confused with distinguishable and indistinguishable states, don't worry, it's going to be a bit clearer when I actually run through the conversion, kind of the minimization algorithm. So I have the following example here, and the question or the kind of problem is to reduce the DFA M into a essentially minimal DFA. Okay, so an equivalent DFA with the smallest possible number of states. Okay, so remember the first step in reducing our DFA is to eliminate the unreachable states. And if you look kind of quickly here, you're going to notice that Q5 is definitely unreachable because both of its edges are outgoing and it has no ingoing or incoming edges, okay? So already we see that this is going to be an unreachable state, which we're going to say here. So we're going to remove the unreachable state and all of its incident edges. So we're going to remove Q5 as well as 0 and 1, so as well as its incident edges. Now we have our kind of, we have our equivalent intermediate DFA that no longer has any unreachable states. What we're going to do now is we're going to initialize our two partitions, S1 and S2. Remember, S1 is the set of non-final states, or Q minus F. So in this case, the non-final states, or in other words, the states that don't have a double circle, are Q0, Q1, and Q3. Okay. Then our second partition, S2, is going to be for the final states. That's going to be Q2 and Q4. So we have our two initial partitions, S1 and S2. Now what we want to do is for each partition and for each pair of states, we want to check if they are distinguishable or indistinguishable. Okay, so why is the distinguishable, indistinguishable thing important? Because let's say Q0 and Q1 are distinguishable, meaning they're kind of different, then what would happen is we would separate the partition. Okay, so we would split the partition. If instead they were indistinguishable, like for Q2 and Q4, if they were indistinguishable, then in the next step, we would keep them together. Okay, and essentially we would repeat this process for each pair. So if perhaps, let's say Q0, so maybe let's not look at this line yet. Maybe Q0 and Q1 are indistinguishable, or sorry, they're distinguishable, so they go in different partitions. But then maybe Q3 is indistinguishable with Q1, then it would go with Q1. Okay, I mean, this isn't what happens in this case, but it could in another DFA occur. Okay. What doesn't happen though, which some students, some students might have the question is, you don't, once you're in different partitions, you're not going to check states, pairs of states, where one state is in one partition and another state is in another. So you're never going to go back and merge again. So in other words, you're not going to be in two distinct partitions and then merge back again. So this never occurs in this kind of algorithm, okay? So that's the idea. Now let me actually run you through the computation. So I have this, not the extended, I have this transition function delta that I've made into a table just because I find it's a bit easier to do it when we have kind of a tabular view of it. So we start with our two partitions, S1 and S2. And remember, so for each partition and for each pairs of states in each partition, we check if they're distinguishable or indistinguishable. So what I'm going to do is I'm going to start with Q0 and Q1. Okay, so I have Q0 and Q1 here. This tells me, this is the delta that says, so how you would read this is delta Q0 when it sees a 0. So this is the Q0 here, this is the 0 here. When it sees a 0 and you're in Q0, you go to Q1. So this would be Q1. And that's how you would read that, okay? So now, if I'm in Q0 and I see a 0, I go to Q1. Q1 is part of partition S1. So I write that's in S1. I compare that to Q1 when it sees a 0. So if you're in Q1 and you see a 0, you go to Q2 as it says here. Q2 is part of partition S2. So this is going to be in S2. So already we see that Q0 and Q1 are going to be distinguishable. They're distinguishable because for the symbol 0, Q0 and Q1 are going into two different partitions. So these partitions are different. These are not the same. So this implies that Q0 and Q1 are distinguishable, okay? Meaning that for now, what would happen, what I would do is I would say Q0 and Q1 are part of two different partitions. I don't immediately close these, and the reason for that is now that I'm going to check Q3, it's possible that Q3 is indistinguishable with Q0, so then it would go with Q0. If it's distinguishable from all the others, then you would kind of close each one because each one would be separate or kind of different from all the others, okay? But we're not there yet. At this point in my kind of explanation, the only thing that we know is Q0 and Q1 are in different partitions. Now, let's compare Q3 with Q0. So I'm going to erase this. I'm going to keep the partitions because for now the partitions stay the same, right? So if you're in Q3 and you see a 0, you're going to go in Q4. Q4 is part of partition S2. So I know that for Q0 and Q3, immediately I already know that these two guys are going to be indistinguishable because the partitions for when they see a 0 are different, okay? So I already know that Q3 is not going to go with Q0. So essentially what I can do is I can close the partition for Q0 because no other state can go with Q0. Okay. So now I have two options. Either Q1 is going to go with Q3 or Q3 is going to be alone and Q1 is going to be alone. And to check that, I need to check whether Q1 and Q3 are indistinguishable or distinguishable. So again, I'm keeping the partitions because for now they're the same. Now I'm going to compare Q1 and Q3. Well, for for the symbol, input symbol 0, it appears that the partitions, well, it doesn't appear. It is, in fact, true that they go to the same partition S2. So for now, it might look like, or it appears that the states could be indistinguishable. But now to confirm, we have to do all of the symbols. So the second symbol here is 1. So now let's check for Q1 and Q3 what the partitions are when they read a 1. So when Q1 sees a 1, it goes to Q4. I know that that's part of S2 because that's what I've labeled the partition Q2, Q4 as. When Q3 reads a 1, it doesn't go into S2, it goes to S1 because Q1, because it goes to Q1 and the state Q1 is part of partition S1. So for one, they go to different partitions because for at least one symbol, they go to different partitions. They are distinguishable, meaning that this scenario does not occur. In fact, it is this scenario here that occurs. So Q1, Q0, Q1, and Q3 are all part of different partitions. Now we need to compare for Q2 and Q4. Remember, we're not going to compare between partitions. We're comparing each pair. So for each partition, we're doing for each pair in that partition, okay? So the only pair in the partition S2 is Q2 and Q4. Okay, so maybe let me clean this up a bit. Yeah. So actually, let me just, because it's going to be different partitions anyways. So when you're in Q2, you see a 0, you go to Q4. That's part of S2. When you're in Q4 and you see a 0, you go to Q2. That's part of S2 as well. So far it appears like they might be indistinguishable. Again, if you're in Q2 and you see a 1, you go to Q4, so you go to S2. If you're in Q4 and you see a 1, you go to Q2, which is also part of S2. So again, for a symbol 1, they go to the same partition. Notice that it didn't need these two partitions, like the partition that they go to for 0 and for 1, they don't need, so need not be the same. Okay, this could have been S1 and S1, and that would have been fine. Okay, but it just so happens that in this case, they both go to S2. Okay. So what does that mean? Well, that means that for each symbol 0, 1, the pair Q2 and Q4 go to the same partition. So Q2 and Q4 are indistinguishable, meaning that in the second step here, so in this step here, they're going to be part of the same partition. So the algorithm isn't done yet. We need to rerun it and check again. So we need to relabel our partitions. Now I have 3, so I make 4 partitions, sorry, so I have 4. And I need to check for each partition whether there's again going to be some splitting, okay? So it's going to be easy for S1, S2, S3. They only have one state. So of course, they're not going to split anymore because there are no pairs in S1. So I know I can directly just rewrite these 3, okay? The only one that I need to check is I need to check for S4. Maybe Q2 and Q4, once we're here, they're going to split. Maybe they're going to stay together. So that's the only thing I need to check. So in fact, let me just erase this. In fact, what's going to happen is when you see Q2 and you see a 0, you're going to go to Q4. Instead of that being called S2, this is now called S4. The same thing for Q4, when it sees a 0, it's going to go to Q2, which is a 4, which is S4. And again, the same thing for when they read symbol 1. So in fact, it's the same. When they read symbol 0 and symbol 1, they go to the same spot. So it shouldn't surprise you that this is again, this is what? This is partition S4. Okay, so for each symbol, they go to the same partition. So meaning that, again, they are indistinguishable, so they stay together. And as soon as there is no change, in this step-by-step algorithm, you terminate the process and you essentially stop. So the minimal states have been identified. The last thing that you need to do is you need to actually convert this to a DFA. And what you do to do that is you take each set or each partition of states and you make that a state. So for instance, partition Q0 becomes a state, partition Q1, partition Q3, and partition Q2, Q4. Okay, so the partition that contains the initial state is going to be the initial state, and then okay, and then the states that contain final states will be final states. Okay, and remember here, Q2 and Q4 are the final states. It just so happens that at the end they're again together. So we again only have a single final state. That single final state is going to be this guy. If, for instance, if Q2 was maybe here, then these two states would have the kind of final states. So then this guy would also be a double circle. But here, again, as I just said, it just so happens that there is only one state that contains final states from the initial DFA, and that's this guy here, the partition Q2, Q4. And then the transitions, you only need to follow this table here. You follow this table here, and because the indistinguishable states are grouped together, it doesn't matter if Q3 goes to Q2 or Q4. When it sees a 0, you would make an arrow that goes like that, okay? So what do I mean by that? Well, when Q0 sees a 0, it's going to go to Q1. So it's going to Q1 or partition Q1. When it sees a 1, it goes to Q3. Then for Q1, when it sees a 0, it goes to Q2. And when it sees a 1, it goes to Q4. But Q2 and Q4 are part of the same state. So we can just say that for 0 and 1, Q1 goes to the same state, Q2, Q4. Then for Q3, when Q3 sees a 0, it goes to Q4. Q4 is part of this partition here, so you make it go here. And if it sees a 1, then it goes to Q1 here. Okay. And then finally, if you're in Q2 or Q4, well, it doesn't matter which one we look at. They'll both be the same because they're indistinguishable. That was the whole point, is that indistinguishable states, when they read the same symbol, they go to the same place. So that's why we can group them together. That's the whole idea behind the algorithm. So when you're in Q2 or Q4, you go back to Q4 and Q2. So essentially you go back to yourself. And the same thing for when you see a 1, you go back to yourself. So we can do that. Okay. And so this becomes the minimal DFA. So we started with this guy here, and we minimized it to get, instead of six states, we now have 4 states. And that's the smallest possible number of states for the DFA to accept the same language as the initial DFA. Okay, so this algorithm is known to be a bit long and a bit tedious, but once you get it, it's really just routine. So we're going to do an exercise here. Hopefully that'll clear up any other questions that you might have. So I'm going to give you a few, well, again, as usual, I encourage you to pause the video, but I'm going to take a short water break. But before I do that, let me just read the question and sort of tell you what's going on here. So we want to minimize the DFA M. Here we don't have a drawing of the DFA, we only have the kind of tuple description. And that's on purpose because if you have the actual drawing of the DFA, then it's easier for you to do it in kind of table form. Well, I find it easier to do it in kind of using this kind of table, because I think it's easier to keep track of the partitions. So our DFA here we know has 6 states. It has states Q0 to Q5. The input alphabet is, so this is sigma, this is Q. The input alphabet is 0, 1. The transition function delta is presented here. So remember how to read this. If you're in Q1 and you see a 0, so this is delta. If you're in Q1 and you see a 0, you go to Q1. So you go to Q1. So that's how you read that. Okay. So this is given for each one. Okay. We know that our initial state is Q0, and we know that our final states are Q2 and Q5. So these are our final states. And what I'm going to do is I'm going to let you assume no unreachable states. Okay, because I know that checking unreachability, that would make you have to draw the DFA. So don't do that. Just assume for the purposes of this exercise that there are no unreachable states. So essentially start out with step 1 where you make 2 partitions S1. The first partition is Q minus F. So that would be Q0, Q1, and Q3, and also Q4. And then the second partition containing F would be Q2 and Q5. So start from there and then try to apply the indistinguishable, distinguishable idea, and we'll do the solution together. Okay, so hopefully you had some time to take a look at this exercise. I know it's actually a lot longer than it looks. But these minimization kind of questions are known to be kind of lengthy ones in the sense that they take a lot of time. So we had sort of set up our question saying that the initial partitions were S1, Q0, Q1, Q3, Q4, and S2, Q2, Q5. Okay? So what we need to do now is for each pair PQ, so for each partition SI and for each pair PQ, we check whether P and Q are indistinguishable or distinguishable. If they're indistinguishable, then they stay together. PQ stay together. If they're distinguishable, then they split up. They split up. Okay, so let's start with the partition S1. So let's do Q0 and Q1. So if you're in Q0 and you see 0, you go to Q1. The same thing for Q1. Both of these are part of partition S1. So far it looks like they might be indistinguishable because the partitions are the same. Next, for when reading symbol 1, Q0, when it reads a 1, goes to Q3, that's part of partition S1. And Q1, when it reads a 1, goes to Q4, that's part of partition S1 as well. Isn't it? Yes. Okay. So these partitions, again, are the same because for symbol 0, the partitions are the same. And for symbol 1, the partitions are the same. Then Q0 and Q1 are So Q0 and Q1 are indistinguishable. So that means that for now we have that Q0 and Q1 are in the same partition. Perhaps, so I'm keeping it, not closing it yet, because perhaps there are more states that are going to be in this partition. Okay. So now that I've checked Q0 and Q1, let's do Q0 and Q3. Okay, so are Q0 and Q3 distinguishable or indistinguishable? Okay, so I have the partition for Q0 as S1 when it sees 0. For Q3 when it sees a 0, it goes to Q3, which is part of partition S1. So let me erase this. So far, it appears like they might be indistinguishable. However, when Q3 sees a 1, it goes to Q2, which here is part of partition S2. Okay. It's part of partition S2, but when Q0 sees a 1, it's part of partition S1. So we see that these two partitions are different. So Q0 and Q3 are distinguishable. Don't know why I'm writing all of it, but I am. So what that means is that you have Q0, Q1 in one partition, and Q3 is going to be in a separate partition. So it might, I'm still keeping this open because it's possible that Q4 is in here. And I'm still keeping Q3 open because it's possible that Q4 is in here. Or Q4 can be distinguishable from all the others, and Q4 is going to be here. Okay, so there's a couple of possibilities. So, but I know for now that I know for certain that Q0 and Q3 are distinguishable. The next pair that I'm going to check is, if you wanted to do this kind of rigorously, then what I would do is I would do, so what you might actually think to yourself is, why did I immediately say that Q3 is not going to be in here, even though I didn't check Q1? Well, what you need to notice is if Q3 is distinguishable from Q0, so if Q3 is different from Q0 and Q0 is indistinguishable or equal to Q1, then this also means that Q3 is different from Q1. So it's kind of, the argument is transitive in that way. Say, so Q3 is distinguishable from Q0 and Q1. Okay, so I don't need to check Q0, or sorry, I don't need to check Q1 with Q3. Okay. The next thing you could do is you could check, so if you want it to be kind of always rigorous, you could do like Q0 with Q1, Q3, Q4, then Q1 with Q3 and Q4, and then Q3 with Q4. But because that's going to take a lot of time, and I might already know the answer, what I'm going to do is I'm going to check Q3 and Q4. But if you had sort of no previous idea, then I would do the kind of rigorous kind of by sequence way, checking Q0 with Q4 and so on. But I have a feeling that Q3 and Q4 might be indistinguishable. And I can kind of see, because here Q3 and Q4 are in S1 and Q2 and Q5 are in S2. So it might look like they are actually indistinguishable. Okay, so what I'm going to do is I'm going to take Q3 and Q4. Okay, so as I said, when Q3 reads a 0, let me erase this. Q3 sees a 0, it goes to S1, and when Q4 sees a 0, it goes to Q4, which is part of S1. So for here, for the symbol 0, Q3 and Q4 go to the same partition. Then for the symbol 1, when Q3 sees a 1, it goes to Q5, and when Q4 sees a 1, sorry, it goes to Q2, which is part of partition S2, and when Q4 sees a 1, it goes to Q5, which is part of partition S2. So again, for the same symbol, a 1, these are part of the same, these are going to be the same partition, okay? So because for 0, they're in the same partition, for 1, they're in the same partition, Q3 and Q4 are indistinguishable. So that means Q3 and Q4 go together. And there's no way that Q2 and Q5 are going to go with these guys. So I can now close these two guys. Okay. Then the last thing I need to check, because I've checked essentially by doing this, I've already done all the pairs in S1 because they would always give this result no matter what. So now I just need to check the pair in S2. So I need to check if Q2 and Q5 are indistinguishable or distinguishable. Well, we can actually see it quite quickly. Q2 and Q5, when they read a 0, they both go to Q0. So they go to the same symbol. They go to the same place, the same state, actually not even the same partition, the same state. So of course, they're going to be in the same partition S1. Okay. And then for 1, when Q2 and Q5 see a 1, they both go to the same state again. So of course, they're going to be part of the same partition, in this case, S2. So they are indistinguishable. So again, that means that Q2 and Q5 are going to be together. Okay, so that was the second iteration, or I guess the first iteration of that process. I need to essentially repeat the same process again for each partition and for each pairs, for every pair in that partition, check indistinguishable or distinguishable. So what I need to do now then is I need to relabel these S1, S2, S3. And now I need to check, so now this is with S1, S2, S3. I need to check Q0 and Q1 indistinguishable or distinguishable. Okay? Because it could change. It could change because perhaps when I repartition them, maybe Q0 goes to one partition and Q1 goes to another partition. So I need to double check. When Q0 and Q1 see a 0, they both go to Q1, so they, of course, go to the same partition S1. When they see a 1, they go to Q3 and Q4 respectively. That is part of partition, those are both part of partition S2. So for symbol 0, they go to the same partition, and for symbol 1, they go to the same partition. They are then indistinguishable. So they're indistinguishable, so that means that they're going to be together. And I'm going to close them up because you can't add any new states to them, right? I do the same thing for Q3 and Q4. So for Q3 and Q4, when they see a 0, they go to Q3 and Q4 respectively, which is part of the same partition as 2. And then when they see a 1, they go to Q2 and Q5 respectively, which is again part of the same partition, but this time it's S3. So these two are the same for symbol 0. These two are the same for symbol 1. So that means that Q2 and Q5 are indistinguishable. So that means that they would go, sorry, not Q2. I got ahead of myself there. That means that Q3 and Q4 are indistinguishable. So they would go in the same partition again. And finally, the same thing we would need to check for what? Q2 and Q5. Oh, whoops, let me do this. Q2 and Q5. I check the same thing. For Q2 and Q5, they go to the same state. So of course they go to the same partition. And let me just clean that up. This partition being, in this case, S1. Right, because I just called S1 the partition containing Q0. So I'm going a bit faster because, again, this is pretty repetitive once you start seeing a pattern. And then for Q2, Q5, when they see a 1, they'll go to Q2. But they'll both go to Q2, so of course they'll go to the same partition. In this case, that partition is S3. So again, Q2 and Q5 are indistinguishable, so they go together. And so what's happened here from this step to this step, no change. So that means that we can terminate this kind of iteration. And now all that's left to do is actually draw, I'll draw it here actually, is to draw the minimal DFA. So remember, the states are the partitions, or the final partitions. So let's say 0, 1 is one partition, 3, 4 is another partition, and 2, 5 is another partition. The initial state is the state of the partition that contains the initial state. So in this case, 0, 1 contains the initial state Q0. So that's going to be the initial state. The final states, remember, were Q2 and Q5. These, again, happen to be in the same state 2, 5. It could have happened that, well, no, it couldn't have happened that 2 was with 3, but it could have happened that 2 and 5 had split, so you would have 2 final states. So remember, I just said 2 couldn't have gone with 3, 4, and that's because if you're in different partitions at the beginning, you're never going to merge again, okay? So that means that 2, 5 is going to be the only final state. And then it's pretty simple for the transitions. I just read it off the table here I have. So for 0 and 1, once they see a 0, they both go to Q1, so they just go back to themselves. When they see a 1, they go to 3 and 4, but 3 and 4, because but 3 and 4 is part of the same partition. So that's 3, 4. Then for 3, 4, so for 3 and 4, when they see a 0, they go back to themselves, 3, 4. When they see a 1, they go to 2, 5. So they go to 2, 5. Then for 2, 5, when they see a 0, they go back to 0, so they go back to this partition. And when they see a 1, they go to 2, 2, so they go back to themselves. And this would be your minimal DFA. So in general, given any question that says you're given a DFA and you want to minimize it, this is how you would this is one way of doing it with this kind of tabular approach that I personally like, because it's less easy to get mixed up, I find, if you do this kind of method rigorously and you kind of separate each step, renaming the partitions accordingly. I find that it's doable. Okay, there of course might be different ways that you're more comfortable with, and that's fine. This is just one way that I thought would be good and would be fine for doing this, and this would most definitely give you, if you show the process. So definitely in your assignments, when I was a marker and when I was marking questions like this, some students didn't show any steps. Definitely show steps. If you show steps, something like this, and you get your minimal DFA, you'll definitely get full marks for that question. Okay. So yes, this is it's a very bold promise, but if the marker you have is sensible, then this should definitely give you full marks. Otherwise, I would try to ask the marker for clarifications. Okay, so the last question in this part of the tutorial is a kind of the same question, but also slightly different. We want to find a minimal DFA M for the language L here. So we're given this language L, and we want to find the minimal DFA. So this is not the same as taking a DFA and converting it to the minimal DFA. So what we need to do here actually is, the first thing we need to do is find a DFA M such that L of M, so the language accepted by M is L. And the second thing we need to do is minimize M, okay, using the state reduction algorithm, okay. So what I'm going to do, I'm just going to do step 1, because as you've already seen, minimization takes a lot of time, so I'm going to leave 2 as an exercise for you. This is a slightly different DFA DFA construction that we haven't looked at yet. So I thought it'd be nice if I did it myself sort of for you. But if you want, again, I always encourage you to pause the video, try it yourself, and check back. So on pause, I guess. Okay, so hopefully you had some time to look at it. The first thing, again, that we want to do is we want to just find a DFA that accepts the language. So what's the language? The language consists of two sort of finite, well, two strings, B and BA, and then kind of a constructive set, A and B, where N is strictly greater than 0. So in other words, it's B, BA, and then AB, A2B, 3B, and so on. Okay, so let's try to construct a DFA that accepts this language. So if you start at your initial state Q0 and you read a B, then let's call that Q1. That should be a final state because you want to accept a B. Okay, so that takes care of B. Okay, then if you're in Q1 and you see an A, then that's going to be for BA. So you're going to make that a final state as well. So I'm going to do this maybe piece by piece, and then for each state, I'm going to check that because we're assuming sigma is AB. I'm going to check that each state has exactly two outgoing transitions, one for A and one for B. Okay, so let's go back to Q0. What happens if you see an A? Well, if you see an A, you don't accept yet, but it's possible that that first A is for AB or A and B. Okay, so if you see an A, then you're not accepting yet, but when you're in Q3, you check whether or not you're looking at more than one A. So, because remember, what you're doing here is you're checking for any number of A's. If you have any number of A's followed by a B, you should accept. So to do that, you read an A, and then if you have any number of A's, I can do this because notice N is greater or equal to 1. If you have any number of A's followed by a B, then this should be accepted. So this branch here gives me A and B. This guy gives me B, and this guy gives me BA. Okay, so that means that I have my language here. The rest is just essentially cleaning up and sending things to a trap state or a dead configuration. So for Q0, I have my two transitions. If I'm in Q1 and instead of seeing A, I see a B, well, BB or anything like that is not going to be accepted. So that's just going to go into a trap state, which I'm going to call Q5. If you're in Q2 and you see an A or a B, that's going to look like B, A or B. That's not like anything in here. So that's also going to go into a trap state. And the same thing for Q4, anything that you see, so A and B, A or B, that's also going to be rejected. So that's going to go A and B. Okay, so this is a DFA M such that L of M is equal to M. You might have L of M is equal to L. You might have found another one that maybe has a larger number of states. But the idea here is now that you have this DFA M, what you want to do is we want to apply the state reduction algorithm. So remember, step 1 is removing all unreachable states. Here you can definitely see that there are no unreachable states. The second step is you initialize your partitions S1 and S2. S1 is a non-final state, so it's Q0, Q3, and Q5. And S2 is the final state, so Q1, Q2, Q5. Okay, and then from there, you essentially check for each pair in each, so for each partition and for each pair in that partition, check if they're distinguishable or indistinguishable, and then they'll essentially split accordingly. They'll split or stay together accordingly. Okay, but I'm not going to do that because I think 2 examples is already enough to get the idea. I encourage you to do it at home, and we already actually have the answer here that's given, so you can just double check with this. So I'm actually recording this at the end of July, summer 2020. So this was after the Comp 335 course ended. And so what I'm thinking, I don't know if this will really happen, but what I'm thinking is I could maybe post these tutorials on a Google Doc that just students could access. I'm still not sure though. I don't know if I need to check with the university or the professor for copyright infringements. So if you don't see a Google Doc, then that's probably why. If you do, then that's great. I hope it'll be helpful. But that concludes that concludes the section on the minimal DFAs. Hopefully this was clear. Hopefully this allows you to do some of the assignment questions. And if it wasn't explained very well in the lecture, hopefully this has kind of shed some light. My ultimate goal is to try to be helpful in these videos. Yeah, so I really do hope that that's what's going on, that these are being helpful. So enough about me. Take care, everyone. Stay safe, and see you in the next video.